Yeah.
That's not very much.
Okay.
Like what?
Sorry.
I was married.
Oh.
If I have
No.
Webster was 60.
a curve, okay? So far we have talked about critical points, okay?
Yeah.
And on a continuous curve like this, the critical points would be where your instantaneous slope is equal to 0. So this would be a critical point, whatever the x value is here, and this would be a critical point, whatever the x value is there. This would be a relative max
Min.
and relative min, okay? The only way they would be absolute maxes or absolute mins is if I did what?
Changed it to
Close and interval.
Local or relative, both are fine.
Okay.
Yep.
Just making
Okay.
sure.
if you didn't have it continuing, like if you put a dot instead of a
Correct. If I closed the interval to right there, basically, if I said, let's only look at this closed interval from A to B,
Yeah.
find the extreme of. Well, then you would call this an absolute max, and call that an absolute min. Because on a closed interval, there's always an absolute max and an absolute min.
monkey man.
Okay.
Just cut out
Now, if we go back to the physics stuff that we did earlier on, when we talked about the movement of an object, we talked about its velocity. And if the velocity was positive, it's going forward. If the velocity is negative, it's going backwards. Okay. But when the velocity started, the rate of change of the rate of change, or the derivative of the velocity, we started getting into acceleration. Okay. So it's how fast the velocity is changing, or the rate of change of the velocity. Okay. Well, on a graph, we're going to talk about the rate of change of the slopes. Okay.
So how fast the slope is showing?
So the slope right here is positive. Slope right here is positive, but a little less. So would you agree with me? The rate of change is decreasing.
Yes.
The rate of change is still decreasing. The rate of change is still decreasing. Still decreasing. Got to 0. Still decreasing. Still decreasing. Till about maybe somewhere in there, right? Because it was positive, a little less positive, a little less positive, got to 0, negative, 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 got to this extreme negative value, but then it starts coming back up, getting closer to 0 again. Okay? That is called an inflection point. That is called an inflection point. It is where the rate of change of the rate of change switches, okay, from decreasing to increasing. But what we're going to call it, or talk about, is its concavity. From the beginning of this graph to right there, that graph is concave down. Okay? Huh?
The home's actually up, but whatever.
Okay? It's concave down. It's opening towards the down part. Okay?
Would it ever be called convex up?
No. Okay? And then from here all the way over, now it's concave up, meaning it's opening up. Okay? And that also means then, if it's concave up, it means the instantaneous rates of change are increasing. Because here it's pretty severe negative, getting a little less negative, getting a little less negative, now it got to 0, and now it just keeps increasing really fast. Okay? So we got concave down, concave up. That's the inflection point, and inflection points are where a graph switches from concave up to concave down, or vice versa. Okay? How do we find those? Second derivative. Okay? Second derivative. When the second derivative equals 0, those are your inflection points.
Sweet.
Once you know your inflection points, all you do is you plug numbers into the left of that inflection point, plug numbers into the right of that inflection point. If you get a positive, it's concave up. If you get a negative, it's concave down.
Sounds simple enough.
So it's very, very similar to your first derivative test, where you see if something is increasing or decreasing. This is called the second derivative test, and it determines whether something is concave up or concave down. Okay? So Maybe I'll do an example here with. Did I start the video?
I hope so.
Yeah.
Yeah.
Maybe.
Yeah, you're like 5 minutes in.
Okay, good. All right. So yes.
Can you repeat what you said about plugging in points and that influencing whether it's concave down or convex or concave up?
You know how we do with the increasing, decreasing on a number line? We plug in points in certain places and see if we get a positive answer for the first derivative or a negative answer to the first derivative.
Same thing.
Same thing, but with second derivative, and it just determines whether it's concave up or concave down. If you get a positive, it's concave up. If you get a negative, it's concave down.
You said our inflection point is
Where the second derivative equals 0. Yep. Okay?
0 and 2.
Alright, so in this case, our first derivative would be
4x to the third
Minus
12x
squared.
squared.
okay, 4x to the third minus 12x squared. That'd be your first derivative.
Oh,
If we wanted to,
Stop.
we could set that equal to 0, find our critical points, find our maxes, find our mins, find its increasing, find its decreasing intervals. We could do all those things. Okay? We're strictly working on inflection points right now, and inflection points are where the second derivative is equal to 0.
So 12x squared minus
12x
24x.
squared minus
24x.
24x.
You guys had such lovely participation. Everybody appreciates it.
I can tell.
So
Okay.
0 and 2.
You're
So,
jumping the gun again.
so then, we take our second derivative, we set it equal to 0, and we solve. I'd probably take out a 12x, and you get x equals 0 and x equals 2. Those would be your inflection points.
Boom. That was easy.
Why'd you say achieve before you speak?
He's preparing.
Next time we'll say bless you after that. Just so the situation makes less sense.
Would be 1.
So then we put those on a number line?
Yep, we'll put that on a number line. Again, just to make sure you have it, I don't know what you've written down in your notes, but inflection points, they occur when f double prime of c equals 0, so when the second derivative equals 0, or also when the second derivative does not exist at c. So just like with the first one. Or when the second derivative, f double prime, or when the second derivative does not exist at c. Okay? So that's how you find your inflection points. Check to see when the second derivative equals 0, or when the second derivative does not exist. Those will be your inflection points.
What if you have a situation where it equals 0 and does not exist? Well, you're screwed. Would you have 2 inflection points?
Oh.
I don't know how. I mean, that is crazy like that. But I didn't think that could help.
Think, if it's 0, it's 0. If it does not exist, it can't be 0. Because it does not
Negative
exist.
Don't we also have to figure out if it's concave up or down?
Yeah, what if we have negative?
Okay? So,
0.
we had 0, we had 2.
Wait.
My second derivative was, I'm going to write it this way, 12x times x minus 2. And that was my second derivative.
Yeah.
So again, I'm going to test points If I plug in a negative number,
You get
that's a negative, that's a negative,
Which is a positive.
so therefore positive. Between 0 and 2, I'll just test 1,
That's smart.
positive,
Negative.
negative,
Right.
right?
I thought you do the same amount of.
What?
So why'd you
Like
do
you
3
did
pluses
3
and
positives,
then 4?
but then 4 negatives? Why do you do
I don't
that?
think that
That's
matters.
exactly
It's
what I
There
just
was more space.
No, there's not.
So then you need to do a ton of the next.
Okay, 3 positive, positive. Watch this.
I like it.
No.
I know.
so going from positive to
Should've done
negative
one of them.
is
You
up
should've
or
just
down.
said-
Okay, so what this means is from negative infinity to 0, the graph is concave up.
Okay.
Because it's
Okay.
plus or
Oh,
minus?
it's side. Okay.
No, because I got a positive
Oh,
number right
duh.
there. Yep.
Duh.
Okay, so it's concave up from negative infinity to 0, and then it's also concave up again from 2 to infinity.
So it's not between. Okay, that
Okay.
makes sense. And then it's down from 0 to 2.
Concave down from 0 to 2. And then at 0 and 2 were the inflection points.
Is that all we're doing?
Okay?
So would we just put like x equals 0?
If they did ask for the specific point, you would have to plug 0 back into the original function and 2 back into the original function. So I suppose officially, if that's what they ask for, find the points of inflection and discuss. So, yes. These are the x values of the inflection points. The actual inflection points would be 0, 0, 2, 16 minus 32, negative 16. No. Yes. 16. Yeah. Okay. The graph of this function.
Just a squiggle.
It's like this. Okay, roughly.
I love that graph.
But right in here, okay, right in here it's concave up. Remember we had an inflection point right here. Because for this part of the graph it was concave up, but once it got right here, this part of the graph right here,
It's concave
that
down.
part's concave down. Then once we got to, what was it, 2 or something? Once it got to 2, so that, roughly somewhere in there, I know I didn't draw it to scale, alright? But once we got to right here, it switched from being concave down to now being concave up.
Could sketch that at all, maybe.
Okay, what's that?
Could sketch that all in the test.
No, you wouldn't have to. This would be another thing where, again, I'd probably enter the graph into my graphing calculator to confirm that it makes sense. Whatever intervals I'm writing down as my answer, it looks like that's right. It looks like it's concave up from negative infinity to 0, like we said, and then again from 2 to positive infinity, it looks like it's concave up, and then from 0 to 2. So it's just kind of a confirmation type deal with the calculator. Right.
Is anything ever convex?
No, we'll just call it concave up, concave down. Okay? So that's about the concavity. Critical points. It's the second derivative test.
Oh, yes.
So on the test, is it gonna ask us to find like everything? Is it gonna
Yeah.
So will it be one problem where you do first derivative, all
Yeah.
the stuff that goes with that?
Basically, one problem, you do everything.
So is there only gonna be one problem?
So get it one problem test.
So one problem
Maybe
C12?
trig at all?
Huh?
Any trig on it?
Not on the test, no.
Thank
What about
goodness.
for the story problems?
There's all.
Oh, yeah.
There's always.
Do I have to take,
Yes.
I can't. Oh, God.
Because if you fail it, then.
Just ace this one.
Well,
then
you
you
say
don't have
ace
to
this
take it
one,
the
then
third
you
time.
fail a third time, that is so.
wait, we're taking that one 3 times?
Yeah, 6 people did it fail.
Okay. So homework today, page 195.
We don't take 3 times. I see how it is. John's gonna go back. He doesn't want me to get back.
I can't imagine why.
Oh! Because I'm better than him at math, and he only got an A- in calculus.
As I said, I can't imagine why.
Because he's jealous. He's a hater.
Hey, John, scoreboard.
Wasn't what I was thinking.
Um, work on this, have questions about this going forward. Tomorrow, big review day,
Awesome.
okay? Now, we also found,
Let's do a lot of repetitive grades.
Yeah, so a lot of C11, a lot.
Like, the exact question
Like-
on the test.
Like,
just-
similar
3
wording.
pages of them.
Yeah, that would be great.
Yeah.
What are those?
No.
Oh, story problems.
Like, what are these?
Which one should I circle that I know
This is
people
what I
know?
should-
Yeah, would you tell us which ones we need to
Nope. All of them.
look at
Let's put her
specifically?
speak. I don't speak that language.
Okay.
John doesn't need. We got extra, by the way.
John doesn't need
You need the extra pack, Ralph.
No, maybe she got extra.
Maybe
So-
I'll